Let's have a little bit of a review of what a function is before we talk about what it means, what the domain of a function means. So a function we can view as something, so I'll put a function in this box here, and it takes inputs, and for a given input, it's going to produce an output, which we call f of x. So for example, let's say that we have the function, f of x is equal to 2 over x. So in this case, let me see. So if that's my function f, if I were to input the number 3, well, f of 3 that we're going to output, we know how to figure that out. We've defined it right over here. It's going to be equal to 2 over 3. It's going to be equal to 2 over 3. So we were able, for that input, we were able to find an output. If our input was pi, then we input into our function, and then f of pi, when x is pi, we're going to output f of pi, which is equal to 2 over pi. So we could write this as 2 over pi. So we were able to find the output pretty easily. But now let's do something interesting. Let's attempt to input 0 into the function. If we input 0, does the function tell us what we need to output? Does this definition tell us what we need to output? So if I attempt to put x equals 0, then this definition would say f of 0 would be 2 over 0. But 2 over 0 is undefined. Let me write this. 2 over 0. This is undefined. This function definition does not tell us what to actually do with 0. It gives us an undefined answer. So this function is not defined here. It gives a question mark. So this gets to the essence of what domain is. Domain is the set of all inputs over which the function is defined. So the domain of this function f would be all real numbers except for x equals 0. So let me write down these big ideas. This is, so domain. A domain of a function. Actually, let me write that down. Domain of a function. A domain of a function is the set of all inputs over which the function is defined. Over which the function is defined, or the function has defined outputs, over which the function has defined outputs. So the domain for this f in particular, so the domain for this one, if I wanted to say its domain, I could say, look, it's going to be the set, and this curly brackets, these are kind of typical mathy set notation. I can say, okay, it's going to be the set of, and I'm going to put curly brackets like that. Well, x can be a member. This little symbol means a member of the real numbers, but it can't just be any real number. It can be most of the real numbers, except it cannot be 0, because we don't know this definition. It's undefined when you put an input a 0. So x is a member of the real numbers, and when we write real numbers, we write it with this kind of double stroke right over here. That's the set of all real numbers, such that, but we have to put the exception. 0 is not x equals 0 is not a member of that domain, such that x does not equal 0. Now let's make this a little bit more concrete by doing some more examples. The more examples we do, hopefully the clearer this will become. So let's say we have another function. And just to be clear, we don't always have to use f's and x's. We could say, let's say we have g of y is equal to the square root of y minus 6. So what's the domain here? What is the set of all inputs over which this function g is defined? So here we are inputting a y into function g, and we're going to output g of y. Well, it's going to be defined as long as whatever we have under the radical right over here is non-negative. If this becomes negative, our traditional principal root operator here is not defined. We need something that, if this ended up being a negative number, hey, well, how do you take the principal root of a negative number? And we're just saying this is kind of the traditional principal root operator. So y minus 6 needs to be greater than or equal to 0 in order for g to be defined for that input y. Or you could say, add 6 to both sides, y needs to be greater than or equal to 6. Or you could say g is defined for any inputs y that are greater than or equal to 6. So we could say the domain here, is the set of all y's that are a member of the real numbers such that they're also greater than or equal such that they're also greater than or equal to 6. So hopefully this is starting to make some sense. And we're also always used to functions defined this way, but you could even see functions that are defined in fairly exotic ways. You could see a function, let me say h of x. H of x could be defined as, it literally could be defined as, well, h of x is going to be 1 if x is equal to pi, and it's equal to 0 if x is equal to 3. Now what's the domain here? And I encourage you to pause the video and think about it. Well, this function is actually only defined for 2 inputs. We know h of pi. If you input pi into it, we know you're going to output 1. And we know that if you input 3 into it, h of 3, when x equals 3, you're going to let me put some commas here. You're going to get a 0. But if you input anything else, what's h of 4 going to be? Well, it hasn't defined it. It's undefined. What's h of -1 going to be? It hasn't defined it. So the domain here, the domain of h is literally, it's just literally going to be the 2 valid inputs that x can be are 3 and pi. 3 and pi. These are the only valid inputs. These are the only 2 numbers over which this function is actually defined. So this hopefully starts to give you a flavor of why we care about domains. Not all functions are defined over all real numbers. Some are defined for only a small subset of real numbers, or for some other thing, or only whole numbers, or natural numbers, or positive numbers, or negative numbers, or they have exceptions. So we'll see that as we do more and more examples.